Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. This video today is not really any C++ language programming per se, but this is our introductory week for the course, and we want to look into binary and decimal and how the two relate to one another. And we're just going to keep track of, integer math here, so we're just going to figure out how to convert between the two. So I have a series of problems. I have 8 of them that I want to solve here. And so I have some algorithms written out. I'll show you how to use the algorithms here to get yourself from A to B or from B to A. So in this case here, I have the number 45, positive 45, and I want to convert that from decimal into unsigned 8-bit binary. So the algorithm that we use to solve this is as such. So I'm going to take the value 45, and I'm going to start from there and I'm going to use the divide by 2 algorithm until I've worked this 45 down until it's a 0. And then, everything will be described here in a moment. And then I'm going to go ahead and take the remainders of the divisions, because everything here is going to be divide by 2, divide by 2, divide by 2. And I'm going to write out the remainders in reverse order. That's why I have this blue arrow here to kind of remind me that I'm not working my way top to bottom. I actually work my way bottom to top. And when I do that, then I'll get the answer. And then if I need to, I'll front pad as many zeros as I need to, throw that in front of the answer so that I get up to 8 bits or 16 or 32 or whatever is asked of me. So 45 divided by 2 is 45 divided by 2 is 22 and a half, or in this case 22 remainder 1. So 22.5. Multiply that by 2, I get 45. So then I bring this number down, and now I do it again. This is 11 remainder 0. 22 divided by 2. 11 is 5 remainder 1. 5 is 2 remainder 1. 2 is 1 remainder 0, and 1 is 0 remainder 1. And that is step 1. I've exhausted everything because now this is a 0. There's no reason to continue because 0 divided by 2 will always be 0 remainder 0. But now what do? I write out everything in reverse order. So my answer would be 1, 0, 1, 1, 0, 1. And of course, I picked the wrong one. This one will read the same backwards and forwards, right? 1, 0, 1, 1, 0, 1. So you might be like, you might be talking to yourself going, did I do it right? In this case, since it's the same backwards and forwards, but I'll do the same in the next example, and I'll prove that that is correct. This 1, 0, 1, 1, 0, 1. And so now I have 6 bits, but this is asking for 8-bit binary, so I have to throw in 2 bits up front. Oops, it will not do that. Let me just, there we go. 0, 0, 1, 0, 1, 1, 0, 1. And so since this is 13 in binary and that is 32, yes, that's how I know it's 45. But again, we'll cover how to work our way backwards in a couple minutes here, in a minute or two, when we show how to basically work our way backwards from 8-bit binary into decimal. So the second part of this here is now to convert the number 207 into unsigned 8-bit binaries, but it's the same exact algorithm. So this is just going to test my math skills. As I get older, they get a little something or other here. So 207 divided by 2 is 103 remainder 1. Okay, and then I take that and I bring this down. And now 103 is 51 remainder 1. All right, so maybe this gets a little easier now. 51 divided by 2, 25 remainder 1. All these odd numbers here, right? 25, 12 remainder 1. Oh goodness, will this ever stop, right? Let's see, 12, there it is. 6 remainder 0. 6 is 3 remainder 0. 3 is 1 remainder 1, and 1 is 0 remainder 1. And so how many bits do I have? 1, 2, 3, 4, 5, 6, 7, 8. Wow, I've used up all 8 of them. I don't need to use step 3 here to front pad. And the answer will be working my way from bottom to top. It should be 1, 1, 0, 0, 1, 1, 1, 1. Oops. me see if I can get that. I don't know how I formatted that number here. There it is. Okay. And so 48. Yep, this is the correct answer. This is 207 in binary. And again, in a couple seconds now, I will show you how to do the reverse, how to take this and convert my way backwards. But that's all there is to it when it comes to this kind of algorithm, especially in, and you can actually, if you end up taking my assembly language classes or if you look through those videos or anything like that, this algorithm can be applied for any, basically to go from decimal to any other system, base 2, base 8, base 5, base 6, base 19. You call it, instead of dividing by 2, you divide by the other values. And surprisingly enough, I could do this and divide by 10 and get 207, because 207 divided by 10 is 20 remainder 7, 20 is 2 remainder 0, and then 2 is 0 remainder 2, and this would work our way back to 207 if I wanted to basically go from base 10 to base 10, from decimal to decimal. So this is a very powerful algorithm. I'm not 100% sure if this is the fastest, most efficient way to do things, but it certainly gets you there, and it doesn't use anything more than just division to get the job done here. Okay, so moving on now, let's take a look at this guy here. How do we go from a binary number and work our way back into decimal? Okay, so I'm keeping this over here for now so I can bring it back for later, so don't mind anything over here. We're only concerned with the actual algorithm here itself. So I'm looking at an unsigned binary number. You have to be told this. That's the whole point of binary. Like, if I'm staring at this, am I looking at an ASCII character? Am I looking at an integer? What am I looking at? Is this an 8-bit floating point number? What is this thing? You have to be told. You can make guesses otherwise, but you wouldn't be 100% certain that the answer you get is correct if you're not told the data that you're dealing with. So this is binary, unsigned binary, and we're going to convert it into unsigned decimal. So I only concern myself with the bits that are ones. Let me just write out the whole thing here. 0, 1, 1, 0, 1, 1, 1, 0. And let me just center this up real quick here. All this, center this. Okay, and then let me give this here. So these are the digits that we're going to, that we're concerning ourselves with. And, just remember how these digits are all laid out. The digit over here is the ones digit, right? So, because it's the least significant bit. And then everything else is powers of 2. Just like if I saw the number, if I wrote out the number 207 like before, you know that the 7 is the ones digit, the 0 is the tens digit, and the 2 are the hundreds digits. And that's how you write things out, and you go, oh, that's 207. And it's it's a little more complicated in binary because obviously 207 can be represented in 8 bits instead of 3 characters. So it would be more complicated to describe, but we could if we had to, or if that was our number system. So everything else is powers of 2 from here. So this is the 2's bit. This is the 4's, and this is the 8's, and the 16's, and the 32's, and the 64's, and the 128's. And so what I'm saying here is you basically only concern yourself with the bits that are ones, because if I multiply all of this, if I multiply 0 by 1, I get 0. So and 0 by 16 or 0 by 128. There's no reason to concern myself with multiplying things by 0 and wasting that time just to get a 0 result. You could if you want to, but you don't have to worry about it. So you find all the ones bits and you multiply the ones, those 2 values. Or I guess you're not really multiplying anything since you're multiplying by 1. So you can just kind of bring down the bits that are the ones down to here. And so here the 2's bit is active, the 4 is active, the 8 is active, 32 is active, 64 is active. And now that you have that, these 3 are inactive because they're zeros. What you can then finally do here is just basically sum everything up. This is 14, and this is 14, 46. This should be 110 if I did this right. Let me just do this so that my skills are not tested. But yes, you get 110 out of this because it's 64 plus 32 plus 8 plus 4 plus 2. So that is how you would go about doing this. And if you wanted to, if you want to kind of remove the if statement from this, if it bothers you that much, I can kind of just do something like this. And I could just set up and just do a multiplication for each of the bits. And as you can see here, and then there they are, the 3 bits, instead of just being wholes, are now zeros because, 0 times 1 is 0, 1 times 2 is 2, and so forth and so on. And you will get the same result, of course. And there's my 110. And so that's pretty much all there is to it to convert from binary into decimal, at least on the unsigned side. So now the next one here, let me just get rid of this. The next problem, say if everything's automated here, but I'm going to get rid of the automation just to show it manually one more time, is a number like this. 1001111. Okay, so that is the number for now. But the same rules apply. So let me just say this is a 1, this is a 0, this is a 0, this is 1, 1, 0, 1, 1. And again, I can just, just delete out the 0 bits and just worry about the 1 bits. And then I can go ahead and sum all of this up. And I get the answer of 155 because this is 128 plus 16 plus 8 plus 2 plus 1. So this is 11, 27, 128 plus 27 is 155. But again, if you want to go back to, basically do the multiplication, you can. Probably the if statement, it'd be a little interesting to see what is slower, one multiplication or an if statement to do these kind of things. And I don't know enough to be able to make a super educated guess on that because they both seem like they could take some time to get the job done. Multiplication takes more time than you think when it comes to calculating on your computer. And it's all relative. How many clock cycles does it take to do the job? Okay, so that covers the first half of everything. This is how you basically do unsigned math from decimal to binary or from binary to decimal. So now we're going to add one extra step to this and say we can deal with signed binary or signed decimal, and we can then represent that value. Because if like this number is 155 unsigned, I guarantee you this number is not 155 signed. This number is probably like -100 or -101 or something like that. Probably, I think -101. But we're going to find out. We're going to do some examples here and see right now. We just, okay. Here are the algorithms to do the signed math. And so the first thing, I know it maybe it's not apparent here, it's not just readily apparent, is that if I tell you it's a signed value, and you can look at it and determine, either way, and you can determine that you're dealing with a positive value, then you basically do the same stuff we just did in the last couple minutes, last 5-10 minutes here. Because like this, the 2, 3, 4 is exactly the same as it was previously, the way I had it. It's only now we're going to add steps to the beginning and end for both of these if we know we're dealing with a negative value. Oops, and and I did write this out, and you go, well, if negative sign is present, I guess you could say like if it is a negative number, and we'll get to that in a minute here. Let me leave this here for now with the understanding that that isn't 100% correct, that I just copy pasted, and that's what happens when you copy paste. Sometimes you forget key details, but we'll be able to determine a negative number in binary in a couple minutes here. Let me just show you. Okay, so -62, step 1. Is the negative sign present? Yes, it is. Disregard it for now. So basically use almost like an absolute value function. -62 becomes +62. And now we do exactly the same stuff as we did before, and now we get to test my math again as I'm talking and thinking and whatever. 62 is 31 remainder 0. 31 is 15 remainder 1. 15 is 7 remainder 1. 7 is 3 remainder 1. 3 is 1 remainder 1. And 1 is 0 remainder 1. Oh my goodness, there's a lot there. And so there is our answer for step 2. And now we write out the remainders of each division in reverse order. So we start from here. We go 1, 2, 3, 4, 5, 0. So 5 ones and then a 0. And I know that's the case because if you add up if you go back, this would be 63 if everything was a 1. So with this gone, it's a 62. But then remember step 4 here, front pad the zeros if you have to. And this is important because again, I have 6 bits here, but I wanted that value in 8 bits. So we have to front pad this. Shoot, I gotta put that dash in front, or that whatever there. And so now we're dealing with this, 0, 0, 1, 1, 1, 1, 1, 0. Okay, so that is, but this is part 4. This is positive 62, right? Coming into a minute here, because that leading bit is a 0, that tells me that this is positive. So I'm dealing with a positive number here. But now, what I have to do, because the negative sign was present here in the original stuff, I have to turn this positive 62 into negative 62. And so the 2's complement is a 2-step operation to finally convert positive 62 into negative 62. And so the first step you do is you basically negate all the bits. It's a bitwise not operation. And then when you're complete with that, then you go ahead and just add 1. It's an increment operation. So it's a not and an increment basically combined into 1. So let me write this out. 0, 1, 0, 0, 1, 1, 1, 1, 1, and oops, I should have moved this over here. 0, 0, 1, 2, 3, 4, 5, and then a 0. And so again, 2's complement is this. Negate all the bits. Zeros become 1s, 1s become 0s. And I think I did that right. And then I add 1 to this. That's not centered. That's not fair. And so now I add 1 to this guy, and this becomes a 0. Basically, 1 plus 1 is a 2, but 2 in binary is 1, 0. So that we carry the 1 over, but now that everything else is the same, now we don't have to worry about anything else. So here, this is your answer. All the bits knotted plus 1. And so the answer comes out to be 1, 1, 0, 0, 0, 0, 1, 0. And that is negative 62 in binary. Let's do more of the same now with negative 115. So step 1, disregard the negative sign if present for now. And then just continue on and do the same method here. So let's see, what is this guy? This is 57, remainder 1. And this is 57 is 28, remainder 1. 28 divided by 2 is 14, remainder 0. I hope I'm doing this right. 14 is 7, remainder 0, and then you get used to these near the end here because they come up very often. 7 is 3, remainder 1. 3 is 1, remainder 1. 1 is 0, remainder 1. So I have 7 bits here. So I have a 1, 1, 1, 0, 0, 1, 1. But we'd have to front pad this because we never got to here. If you wanted to just kind of do it, you could just go 0 is 0, remainder 0. And so now you kind of have your 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So my answer of positive 115 would be 0, 1, 1, 1, 0, 0, 1, 1. And so 1, 2, 4, 8. Well, yep, this is exactly right. This is a positive 115. So now, because this bit is a 0, that would scream out positive to me, because that's the difference here. When I'm dealing with signed binary, I have to look at the leading bit, the most significant bit, and make a decision off of that. And so this is screaming out, this is positive 115. So now I got to use the 2's complement to convert positive 115 into negative 115. So let me just 0, 1, 1, 1, 0, 0, 1, 1. And so now do the not operation, bitwise not. And then add 1 at the end of here. So we end up with 1, 0, 0, 0, 1, 1, 0, 1. That is our answer here. 1, 0, 0, 0, 1, 1. So that should be negative 115 in binary. And so now we'll see on the other side here, how do I convert this? And again, we only deal with it when it's negative. Here is our new problem. Let us take this binary, 0, 1, 0, 1, 1, 0, 1, 0, and let's take that and convert it from from binary into signed decimal. So this is a signed binary value. And so when I'm dealing with this, I'm looking at this, I look at the most significant bit. That is the 0 here in this case. And I go, well, that's a 0 indicates that this is a positive value. So this, you could think of this as a trick question if you really want to, but there's nothing saying, why can't you have Just because I can have a negative value doesn't mean I have to have a negative value. And so in this case, I can disregard steps 1 and 5 because I'm looking at this and I go, nope, I do not have a negative value. And I say, in this case, let me just change this up here. If most significant digit is a 1. If the MSD, I was thinking most significant bit or most significant digit, that's why I combined them accidentally and hilariously. And so, so that's the case there. And the same thing goes here. If I know I'm dealing with a negative value, then I'm going to deal with it at the end. But I'm going to do that in the next problem and not in this problem. So we do things exactly like we did before. Let me write everything out. 2's complement here, right? Or not 2's complement, but just working these things out. It can get tricky. Again, it's only because we're dealing with powers of 2, and I would say I've only grown accustomed. We only grow accustomed to this by practice because it's not something we do every day as humans, but as programmers, people dealing with computers, we end up doing this more often than we think we do. So the same rules apply. If it makes it easier for you, you can just get rid of the 0 bits here. Get rid of everything, and that's what you're left with. 64 plus 16 plus 8 plus 2. So I should get myself 90 if I sum everything up. And I do. Because that's the 64's bit, that's 16, that's 8, and that's 2. So that just summed up. This gives me a positive 90 out of the, that is my answer at the end of the day, is a positive 90. Because I'm disregarding, because there's no negativity here when it comes to the most significant digit or bit here. So let's take a look at the last one here, and that one is turning this value. Get rid of this for the moment, and putting this guy in place. 1 0 0 1 1 0 1 1. Okay, so there's our value. And now when I'm looking at this, I see that the first digit here, the first bit, the most significant bit, is a 1. So I'm going to perform 2's complement right now, right off the bat. So I can turn this negative value into a positive 1. Okay, and so we remember that, of course, we flip all the bits, and my centering went away a little bit. That's okay, we'll fix this up in a second. And then we're going to add 1. Just make this nice for us. Okay, let's see. 1's become 0s, 0s become 1s. We're all good. Now I add 1. So whatever, I don't know what number it is in decimal, right? But I do know that whatever it is, it's going to be this number with a negative sign slapped on the front of it. Oops, I didn't center it. That's okay. 1 0 1. So that's what we're dealing with here. We're dealing with this guy right here, 0 1 1 0 0 1 0 1. Whatever this is a positive value. We're going to calculate it and then just slap a negative sign on the front when we're done here. So 0 1 1, 0 1 1 0 0 1 0 1. And remember, this is the 1s and the 2s and the 4s and the 8s and the 16s and so forths. 64 and 128. And again, if it helps you out, get rid of all the 0 bits. And just sum up everything we've got here. And then you go 101. And then what I see here, and I see this in my assembly language class, and I see this, and I do it too, because you're just like, oh, I'm done. And then you forget step 5, because you did all the hard work. But yes, you are staring at a negative number. So you would, negative. So the answer is negative 101, because that's how it all works out. Because this most significant bit tells me whatever result I get out of this is going to be a negative result. So you'll lose points on that, obviously, because negative 5 is not the same as positive 5. If you've ever taken calculus, or if you ever will take calculus, it's almost the same as missing the plus c when you do spend all the time, all that hard work with your integration, and then you forget the plus c, and then the teachers take off points, your professors and instructors take off points, and you get angry at yourself for forgetting such a simple little thing, taking that final little step and going through it here and adding the negative sign. So that covers everything that I wanted to cover. Unsigned / signed, decimal to binary, and backwards from binary to decimal. So 4 different algorithms here. Notice they both use the same stuff, right? They both use the same divide by 2 method or this multiply out and just sum up everything method. It's just a matter of applying the 2's complement when you have to. And once you can do that, you've pretty much got all of this down pat. And then we can throw in like hexadecimal or octal or any of the other things that we use here, the other bases that we use in computer science. Or if you ever move on to different types of math, you can work in any base system you want, and it's not going to be confusing and scary because you know the ins and outs and the inner workings of it all. So as always, if you have a question or concern about anything I said here, I always make mistakes on here. I try to correct them. Just let me know. Obviously, I'm not trying to trick anybody into making mistakes here. So let me know through email at swardb@cud.edu, or you can obviously comment here on YouTube, and I'll get back to you. It depends on when. If it's during the school year, yeah, I'll get back to you a lot quicker than if it's summertime or winter break or anything like that. But yeah, that covers this lecture. Hope you got something out of it. We're ready to move on to C++ programming next. And so I'm looking forward to that because coding is cool. Coding is fun for me, and hopefully it is for you. And thanks for everybody sticking out with me, and we'll see you next